Okay, good morning, everybody. Welcome to our last lecture of the semester. So we need about 40 more minutes, and we have wrapped up this semester of 402. So congratulations in advance. Our topic today is going to be electrocardiograms. And one last time before we start, I would just love to see in chat that you can hear me, that you can see me, and that all's a go, and we can move ahead. Okay, thank you, Peyton. Thank you, Troy. Good morning to you. So we have seen this idea of cell polarization, and it's brought about by, we have this, kind of wondrous cell membrane that's a good insulator. And this distribution, this imbalance of ions inside and outside the cell is creating this high and low potential region inside and outside. So we have the positive sodium ions on the outside, and that surplus of positive ions on the outside puts that at a higher potential. It's about a 70 millivolt potential difference. As always, the actual number doesn't really matter. It's potential differences again and again and again that would, I've tried to stress this since the very first day that we talked about potential. Really, potential only takes on any meaning when you compare two potentials. And if there's, if they are at the exact same potential, nothing's going to happen. That's kind of, an equipotential line. And if you have a difference in potential, you have the ability to, maybe create an electrical force and impel something between those two potential regions. But the actual number, this zero doesn't matter, doesn't really mean much. It's only when I compare it to some other region in space that's 70 millivolts less than that. And we've seen that, the distribution of ions in a cell inside and outside that membrane is a really efficient way of setting up these kind of significant potential differences. 70 millivolts is nothing, it's not a negligible potential difference. It's a measurable potential difference. And even, in real world circuits, this is something that, would be a significant amount of voltage. So the three phases that we talked about last time as part of this action potential is when the cell is in its resting state, and we have this positive, higher potential on the outside and a lower potential on the inside. And we call that when it's just, polarized. This is the polarization stage. And it's when it's resting. Then it goes through this, very rapid change. And that's by allowing those ions to cross across the membrane, opening up those sodium channels, for example. The sodium ions rush in to that lower potential because they're positively charged, and all of a sudden you have a surplus of potential of charge on the inside, and the potential difference is changed. The sign has flipped. We call this depolarization, and we saw this in the context of a neuron last time. Today we're going to look at this in the context of the beating of your heart, this big muscle in your upper left chest, which is constantly beating and flowing blood to your brain and all your extremities. So after that depolarization, stability is reestablished, or normalcy is reestablished, and we call that the repolarization phase, as we get again a higher potential on the outside and a lower potential on the inside. And this, we saw, that rapid change of potential in one cell can tweak the next cell and cause the same exact thing to happen, that, okay, the cell will depolarize and then repolarize, and then the next cell and the next cell and the next cell. And you have this kind of chain reaction as this action potential flows through groups of cells and kind of propagates as a wave almost through the cells. So what I'm going to do, I'm going to talk today about this process. This is the same exact process that we saw in the axon last time, but in the context of your heart. And I know that a lot of there's at least there's a good number of EMTs in the audience that might have some experience with this directly, some other people that are, you know, on the medical track to become either physicians or nurses or health practitioners of some sort. So I hope that this is something that a good fraction of you have seen in some context or another, or will, you know, in your careers as you go. If you're like me, maybe this is the first time that you've ever looked at this in terms of potentials, and, you know, don't get overwhelmed by the jargon. Again, the actual physics here is pretty straightforward, and it's a pretty straightforward application of things that we've been talking about for several weeks, okay? But I do have to introduce some new jargon. So I'm going to show you, this is a picture of the heart. This is what your heart looks like when you take it out of your chest. It actually looks like a Hallmark card. The top of is called an atrium, or they're called the atriums, the right and left atriums. And the bottoms are called the ventricles, the right and left ventricles. And you can see that there's this odd convention. Actually, it makes a lot of sense that the right is on the left and the left is on the right. Why is that? Well, because for the most part, people that are dealing with the heart are talking, you know, in the context of what's happening to a patient. So if you're a health practitioner and you're looking at the patient, this is the way that it would be. It's kind of this mirror image that, you know, you're talking about the patient's heart. So that would be on the left. The left part would be on your right, and his right would be on your left, that kind of thing. So that's the first part. The heart is electrical in nature. So what we're going to find is, you know, this, it's pumping all the time, contracting and relaxing, contracting and relaxing. And this is kind of a consequence, or not kind of, it is a consequence of this action potential kind of flowing or propagating through the cells of your heart. So where does this start? It starts in something called the sinoatrial node. And the sinoatrial node is this little 1 to 3 centimeter long group of cells in the right atrium. I think sino means right. If I understand my Latin properly, I think that's where that comes from. So you have something, a node in the right atrium, and we call it the sinoatrial node. Who cares? Well, this little node is what kind of sets the pace for your heart. It's where the original electrical impulse, the start of that action potential, originates in your heart. And it triggers that action potential that will then propagate through the rest of the heart. And for that reason, it's sometimes called the heart's natural pacemaker. It's basically what's starting that action potential. And if everything's going right, this is a repetitive, very reproducible, very predictable pattern of this action potential flowing through your heart. And you know, actually the heart does not look like that. It looks like this, as far as I've been told. I luckily have never actually seen a heart, but this is what it apparently looks like. It's gross. And this little sinoatrial node is up here in the left. That's kind of setting the pace for the electrical signals that are going to, you know, control the contraction and relaxation of your heart. Okay. So let's see. What I need to do is, what we'll find is the heart's electric field turns out to be a pattern that we are very familiar with, that we are very fluent with, and have worked with, and had tests with, and done homeworks with, and that's the dipole field. So I remind you, the dipole field is something that at first looks like this horrendous thing, but as soon as you know what's going on, it's not that complicated. You have a group of positive charge and negative charge, you know, separated in space, and the electric field lines flow from the positive and end on the negative. Flow from the positive, end on the negative. That's the blue with the arrows on it. The red are the equipotential lines. So I remind you, the equipotential lines. I just got a message that one of the students had to dissect stuff like this in one of her labs, and it was actually pretty cool. I'm glad it was you and not me, because I really would not like to see the inside of a heart. Or maybe, I don't know. I don't think I would. But I can understand it would be very interesting. So the equipotential lines are these, you know, these lines here, where if you traveled all the way around and measured the potential on these lines, they would give you the same number. So say it's, you know, 30 millivolts, it's going to be 30 millivolts all along this line. If you hop from this line to another line, it's going to be a different value. We can see here that we're getting closer to that positive charge. So this is going to be a larger potential. So if that was 30 millivolts, let's say that this would be, say, 70 millivolts positive. So the last part of this, we talked about this guy a couple of times, I think, in previous lectures. And the last thing that we learned about drawing these diagrams was that the electric field points from higher to lower potential. So we have this electric field line is pointing from higher to lower. So in this particular graph, we have higher potentials over here and we have lower potentials over here. And that's as much as I need you guys to remember about the electric dipole. Okay? So as always, please, if I'm going too fast, even on this last day, or if you have any questions, go ahead, type them in the chat and use that go slow thing, and I'll absolutely pay attention to it. So that's the gist of the physics. Now, how do we overlay this on our knowledge of the heart? Well, let's take a look at the heart again, drawn as a Hallmark card, and what's happening. I want to look at it at a single instant in time. So we have this sinoatrial node, and it's triggering an action potential, and that action potential is rippling across the heart muscle and causing contractions as it goes. We remember when we depolarize, that cell is going to go positive. So we have this region of cells that has gone positive. Their electrical potential has gone higher than it was before. And we have this region of cells that it just hasn't reached yet, and this is still negative. So this line would kind of represent at any moment in time the interface between the positive and the negative regions of the heart. And this is, and again, that's the action potential. So this thing would be moving across your heart. And if I look at this particular moment in time, well, this is kind of the definition of an electrical dipole, is you have a separation of positive and negative charges. So what we're going to find is that your heart is this electrical pump that has these very measurable potential changes as a function of time. And once you record those and get some idea of the normalcy, you can very easily use that as a gauge to see in times of trouble, is there something wrong? Is there something unhealthy about the way that the heart is firing? And basically, diagnose some problems with the heart. So the one thing that I want to point out, I'm following your textbook on this material. And I'll somewhere in the next page or two, I point out the actual chapters. I think it's 20.6 and 21 point something, but it's in the next couple of slides. But your textbook does this weird thing, which I don't like, which is it has the dipole, the electric dipole, point from negative to positive. I just don't think that makes any sense. I like it when the electric dipole points from plus to minus, like we always do electric field lines. And I don't like that they kind of flip that. So I kind of bucked what the textbook is doing, and I'm drawing it the way I want to draw it. If you actually follow in the textbook, all the arrows will point the other way. Makes no difference. It's just a convention, but I hope I don't confuse anybody by that. To me, the vector should go from positive to negative. I don't know why they do it the other way. It's a convention, but I just didn't go along with it. So please don't get confused with that. The other thing that I want to point out is there's nothing particularly special about this direction. At any moment in time, that electric dipole, depending on that distribution of charges, could be pointing left to right. It could be pointing right to left. It could be pointing down to up. Your heart is this complicated thing, and that action potential, I kind of simplified that it just goes in a straight line from the sinoatrial node across the heart. It's a little bit more complicated than that. So at any moment in time, this vector, this electric dipole, could be pointing in any direction, and it could be pointing, it could have a certain magnitude. So that's one little complexity that, I haven't shown yet, but I hope you keep that in the back of your mind. Hey. So, okay, so that's what we got. Okay. So what happens when we have if we actually look at the electric field lines, it gets a little bit more complicated, but again, hopefully something, because you've seen this electric dipole so many times before, all you're doing is overlaying this mental picture of a dipole on top of the heart. And, you know, we have some positive region, we have some negative region. Those electric field lines are going to do this kind of interesting electric dipole type behavior where the electric field lines originate on positive and end on negative. Okay, so we have a region of high potential over here, low potential over there. That's pretty much what I need you guys to take away from this. All right, so let's get to the point of an electrocardiogram. No, you got to turn off that video game. Huh. Hey, Case, you got to turn that off. I'm sorry, I'm teaching right now. Okay, my kid is playing a video game right behind me here. So, oh well. So we have an electrocardiogram, and we're measuring the potential difference across the chest as a function of time. That's the basic idea here. I'm going to present a simplified version of what's going on in a real EKG. In a real EKG, if you've ever had this or you've ever administered one of these, this is kind of, you know, something along the lines of what happens. You have these 6 electrodes placed on your chest, and I think there's another 6 that are placed on your, you know, your arms and your trunk and your legs and stuff like that. And you're measuring the potential difference across all of these pairs of electrodes. We're just going to focus in on a single pair of electrodes and say that my EKG patient here, we're putting one on this shoulder and one on that shoulder, just for simplicity. There's specific places to check specific parts of the heart. This placement is very, very, very carefully done if you've ever had it, you know, have had this administered to you. But we're going to simplify this with, hey, I put one on this shoulder, I put one on this shoulder, and I call this one voltage 1, and I call this one voltage 2. And then all the behavior of all these other electrodes is going to be very similar. So if we understand one, hopefully we can understand what's going on with all of these. So the first thing that I need to do is just point out that if I have this electrode here and this electrode here, and at this particular moment in time, the electric dipole is not lined up with that axis of my electrodes, then all is not lost. It is still very easy to interpret what's going on in this picture. We would have a region in this particular situation where, hey, I have more positive charge on this side of the heart. I have less positive charge on this side of the heart. So I have higher potential over here. I have lower potential over here. And if I think of this dipole moment as a vector, and that's what it is, right? Because if I have a bigger separation of charge, the magnitude of this arrow, the length of this arrow gets larger. And the direction of it depends on how my heart has kind of separated those charges, whether they're at an angle or whether this way, or, you know, where in the cycle of contraction and relaxation your heart muscle is. So, you know, the way to interpret this is I have something that's basically a vector quantity. I can project it on this axis. And all that really matters is that this side, which is closer to electrode 1, is at a higher potential than this side, which is at lower potential, is closer to electrode 2. So in this particular case, if I were to hook up these 2 electrodes on my patient here and then take an EKG at this particular moment in time, the voltage that I measure at electrode 1 is going to be greater than the voltage that I measure at electrode 2. Again, the actual numbers that, you know, are measured at each of those points really has no significance. It's the difference between the two, as always, with potential that is going to be significant. So we have, you know, a higher potential on this guy and a lower potential on that guy. That means I'm going to get a positive value. So you see this thing in the background. This is kind of I think this is a kind of a standard EKG. And sometimes it goes positive, sometimes it goes negative. This would be a situation where we get a positive result in this EKG. So the second situation where I have is when I have a higher potential here and a lower potential here, and the dipole is pointing in this direction. In this case, the potential difference between these 2 points, this is along an equipotential line, And because it's an equipotential line, one second. Because it's an equipotential line, they're about the same. They're the same potential. So you're going to measure a potential difference of 0. Okay, so I hope that that's clear. All that matters in these EKGs is the difference in potential at different locations, as conducted through your, through your chest, through the skin to this, to these electrodes. So what's up? Okay, have fun. Bye-bye. Okay, so what we're going to take a look at is in a typical, heart, there's 3 important parts. I'm sure that there's more subtlety to this to those people who have studied the heart and, have dealt with, the health aspects of the heart. But basically, we have an atrial depolarization. And what I'm going to try to think about is what's happening during these 3 phases: atrial depolarization, septal depolarization, and ventricular depolarization. So in this first, it's a word salad of stuff, atrial depolarization. Again, I don't want to lose you guys in the jargon. All I care about is there's potential differences here, and we understand potential differences. So if I put these electrodes as we place them on this guy right here, and we look at what's happening in this particular case, I have a surplus of positive charge on this side, a surplus of negative on this side, or another way of saying it is I have a higher potential over here and a lower potential over here. So if I take the difference V2 minus V1, I'm going to get a positive number. I can't help you with that. I can't help you with that. I can't. Okay, last day of class and everything's going to heck. So during the septal depolarization, we have things turned around, and we now have the charges are opposite, and we have a higher potential over here, and we have a lower potential over here. So we get a negative number over here, and in the last part, the ventricular depolarization. Again, we have higher potential over here, lower potential over here. Really, okay, you can see that, all that's kind of happening in this little cartoon is the potentials are, the 2 sides of the heart are kind of flipping, whether they're high or low. And that's going to determine whether we're getting a positive signal, a negative signal, or a positive signal. And then the magnitude of how much of a potential difference is occurring is going to be manifested in how big of a voltage difference. This voltage difference is much bigger than that voltage difference. So this is kind of a typical, as far as I know, I'm not a physician, I'm not I'm not an EMT or anything like that. But to my knowledge, this is a kind of a typical electrocardiogram, and then you would have some kind of repetition. And hopefully, if you measured this, this is showing that your heart is operating normally, that there's no there's no loss of rhythm, there's no arrhythmias going on with your heart, there's no kind of electrical problems in your heart that might indicate some deeper problems. So this is a very widely used diagnostic tool, and all it is measurements of potential difference. Okay, so that's really the point that I want to hammer home here is you guys know potential. Electrical dipoles. You kind of really know now, what an EKG does. And yes, an EKG machine has some layers of complexity on top of this. Of course, there's going to be amplification of the signals and cleaning and processing of the signals. But positive potential, positive potential difference, negative potential difference, positive potential difference. That's what's driving this. There's not much more to it than that. Okay? So that's an EKG, and if there's anybody in the audience that has actually administered these or has experience with them, this is, I'd love to hear about it. But what we're gonna do is maybe do a polling, one last polling feature here. So I'm gonna put this up and then get a poll rolling. And hopefully you'll bear with me while I do this. You can read the problem. And so I'm going to launch a poll. And we have a gentleman, there are 3 electrodes placed on the patient. If a heart is polarized as shown at an instant, which the potential difference, at this instant, which potential difference has the largest positive value? So we have 3 electrodes, 1, 2, and 3. And I want you to take a look and think about, which one has the largest potential difference. Okay? So, yes.
Turn the volume from making all the way down.
Shh. I'm still teaching right now. I'm still teaching right now. Okay. Right. There we go. All right. All right. So how are we doing with this poll? I think we got 80% of people are on board. Okay. And I got a comment from the class. How does the height of the lines in the graph relate to the potential difference? Does a larger line equal a larger potential difference? Okay, yes, Fran, nice question. I'll address that as soon as maybe I should address it while we're doing this question, because there's a couple people still thinking about it. Yes, the height, right? This is going to be V2 minus V1. So the height of this is really absolutely proportional to, how big of a difference it is. So what we're supposed to interpret is at C, the ventricular depolarization, this is going to be the point where, the potential difference is the largest. You have the largest change, change from the high to low potential. It absolutely does manifest or mean that a bigger line or a bigger value on this vertical axis is supposed to mean a bigger potential difference, because that's exactly what we're plotting. Okay, so let's end this poll, and I think it looks like the answers were kind of scattered. My results are, most of you chose C, V3 minus V2, and I'm going to have to disagree with you. So again, I don't know how much of this is maybe I'm not explaining it well, maybe how much of it is that my little picture here is kind of crudely drawn. But the idea here was we have an electric dipole going in this direction, which is kind of along the axis of 2 to 1. And because the potential is higher over here, potential is lower over there, we're going to have a big difference between 2 and 1. And I disagree that 3 and 2, this would almost be an equipotential line for 3 and 2 along this direction. So the idea here, we have high potential over here, we have low potential over here, and whatever the difference is between these guys and 3, the difference here to there is going to be larger. So, I'll chalk some of this up to, hey, maybe my picture is just not that clear, and let's try it. We'll try again with a better drawn picture in a moment. So, and Fran, your question, does that address what you were asking? And my other comment here is, it's not fun to walk around with an EKG. I'll take your word for that. I actually had an EKG as part of a physical once, and I did it. I think I was like on a stress test, and I had to run on the stupid treadmill. And I agree with you. It's not pleasant to run with this thing. Can you what? No, you cannot pick a different background. All right. Okay. So let's. I hope I shared those results. So that's what we got. So there we go. So let's, bear with me. We'll try another one here with a better drawn picture as we go. We have a comment here from Sarah. So it's more about directionality along the dipole, not the direction from positive to negative. The reason I chose C was because the charge seems to go from negative to positive, which would give a positive result. Yeah, it's really, you want to think about where's the region of higher potential. And Sarah and Francis and anybody else that was, that landed in the other one, give me a moment here and we'll look at another picture where hopefully this is a little bit more clear and it's not so beholden to my terrible drawing. Fran says getting peppered for an EKG is the worst. They have to clean the skin and oils, and they basically rub it with liquid sandpaper. I didn't know that. That's horrible. I'm sorry to hear that, Fran. Oh, thank you. Okay, so let's try one more here, and maybe in the meantime, I'm going to show a video. This is more along the lines of how do we interpret an EKG? We've seen what an EKG is. It's a potential difference, but if you're a oh, okay. So Fran corrects himself. He was not peppered for an EKG. He was prepared for an EKG. I was kind of wondering, why are they peppering you, Fran? But because they didn't do that to me. But now I see what you're saying. So let's take a look at a video here. Hopefully you guys can hear my audio.
So now let us talk about EKG. It has different parts. We will start with this small bump right here called the P wave, followed by this tall structure right here called the QRS complex. And lastly, the last bump after the QRS complex would be the T wave. Let us discuss them one by one. Let's start off with P wave. The P wave represents atrial depolarization. During atrial depolarization, the two atria are contracting. Next up, the QRS complex. Now, the QRS complex represents ventricular depolarization. During ventricular depolarization, the ventricles of the heart are contracting. Depolarization is for contraction. So how would you know which one is which? That P wave is for atria, while QRS is to ventricles. So if you look at the diagram right here, the QRS complex, it kind of looks like an inverted V. So V for ventricles. So when you see a QRS complex, think about ventricular depolarization. So lastly, we have the T wave. The T wave represents ventricular repolarization. This is when the ventricles are relaxing.
Okay, so I don't want to beat you over the head with that. I just think it's kind of neat that, really it's just potential differences that we're looking at. Let's take another look at, maybe a better drawn picture of what's going on. I need to do single page. So we have here, one of the kind of standard places that you might see an EKG administered is you put one of these electrodes on almost your bicep and one of them kind of on the side of the abdomen here. And here, if we take the potential difference V3 minus V1, hopefully I'm making this large enough so that you guys can see what's going on. And we can have a little bit of a more fair question than perhaps the last one. So one standard location of these pair of electrodes during an EKG is shown. So I'm taking the difference, the potential difference. Again, okay, it's your body, it's your heart, whatever, but it's still a potential difference like any other potential difference. So I hook up an electrode here, I hook up an electrode there, and I'm measuring the difference V3 minus V1. Again, the difference in potential is all that ever matters, not the absolute value at 3 or the absolute value at 1. So our question is, can I get to the next page? There we go. So we get to the next page. At the time shown, will this potential difference V3 minus V1 be positive or negative? Okay, so let me get that poll up and running again. I'll stop sharing the last one. I'll relaunch. And you guys go for it. Okay, so we have, the only difference here is there's a little bit more detail in this plot. Those lines are lines of constant potential. Those are the equipotential lines. But again, we have the negative and the positive. So the higher potential over here, the lower potential over there. So have at it, please. And I think I got another message, so I'll read that in the meantime. And just so you guys don't think I'm talking to myself, you can see what's going on here. I'm running two classes at once. One is you guys, and the other is my kids. I have to, homeschool because of COVID-19. It's kind of fun, but I never planned to be a daycare or elementary school teacher. All right. So Fran asked, is that question asking about the location of the plus minus sign or the dots? Yeah, so the dots are the location of, I'm taking a voltage at 0.3, which is called V3. I'll call that voltage 3. And I'm taking a voltage at 1 at the placement of electrode 1, which is V1. And then I'm going to do V3, which is, some voltage, some number, minus V1. And what I want you to tell me is, if the heart at this instant in time is polarized like this, so that it has high potential over here and low potential over here, is that V3 minus V1 going to be positive, negative, or I don't know? So, okay. Okay, so we got 95% of people. Give a lot, I'll give another 10 seconds here for anybody else that wants to think about it.
Daddy, you make letting people think about it.
Thank you, Mike. Okay, so I got 2 comments from the class. Yes, my daughter is also currently doing her math, which I guess is origami today. So there's lots of questions. Homeschool transition is fun. Sarah, I agree with you. It's kind of, it's not maybe what we plan to do, but I guess it's good to spend time with our kids. So I never thought about that. Probably a lot of you out there in the audience have your own things that you're taking care of at the same time that we're doing this class. So I appreciate, you guys are juggling things. It's always a challenge. So let's take a look. How do we do on this poll? We got 72% saying A, 30% saying B. So the idea here, again, the positive is showing me where, on my electric dipole, the positive part is the highest potential part of the dipole. The negative part is the lowest part of the potential of the dipole. So from here to there, I'm going to have, this is a bigger number than that number. I don't know what it is, but I know that this number is going to be bigger than that one. So this could be 10 and this could be 1, or this could be 29 and this could be 21. The difference is all that matters. So the correct answer is positive A. Okay. We have another comment from a student that says their heart was beating irregularly, like 120 beats per minute, and they wanted to monitor what was happening, so that she had a portable EKG, and it turns out that's just the way that her heart works, and she was luckily able to not participate in gym because of that. So here's a happy story about EKGs. Let's take one more question here. I think you guys are on the right track. If I got 70% of you, let's see if we can get this a little bit higher. One more poll. Let's stop sharing that one and relaunch this poll. Okay. We now have a, same question. I want to know the difference between V3 and V1. Will this be positive and negative? We're looking at a moment later when your heart's doing something a little bit different, and the potential is higher on this side and it's lower on that side. What is the, is this going to be positive or negative? So please go ahead and think about that, and we'll wrap this up. Okay, and you're welcome for clarifying the question. No problem. Okay, looks like I got most of you. Let's do another 10 seconds, think it through, and then tell me what you think. Okay, let's shut this down. So if I can share the results. Yep, this is, most of you get it here. This is going to be negative because at this point we got higher potential on this side, lower potential on this side. It's not perfect, but you could think about projecting this vector onto that axis. That's basically what I'm asking you to do, is kind of think of this as a vector with higher potential on this side closer to the plus and lower potential on this side close to the negative. So what we're going to have is, we would measure a lower number on this side than on that side. So I think most of you kind of get that. So I'm going to skip this final poll, and it's the last day of the semester, so there's no reason why we have to kind of use up every last minute. I think we've had a pretty long and trying semester. I, for one, am ready for vacation. We still have the business of the exam. And I have one last kind of request for you guys. People keep asking me about how's our rescue pup doing. He's doing great. This is Bo. He still doesn't answer to Bo. So I don't know if that's really his name. That's what it came from in the shelter, but he doesn't care what we call him. And he's doing pretty good. Otherwise, he's finally house trained, and he kind of likes to sleep in the cat's bed. But other than that, he's a pretty fun, happy dog. What I'm going to ask you guys to do with this last couple minutes is, you should have gotten, I hope, a notification for teaching evaluations. The last I checked, really nobody had answered those. And yes, this was a weird semester, and I'm just kind of a little bit, I'm cognizant of the fact that maybe I'll have to do this ever again, this kind of online teaching. And I would really value your kind of feedback on what's good, what's bad, because we went into this blind. We kind of threw this online in a couple of days, and I don't know, some parts of it worked, some parts of it didn't. I'd really like to know, your feedback on that, so that we can, if we have to do this again, that we can do it right. Other than that, I really appreciate your patience. I really appreciate the way you guys have engaged in this online format. Somehow I would love to, take that back to the live classroom so that we can keep that, interaction going for the next time I ever teach this. But if you will, please take a look at those, those evaluations. I don't think it takes too long, and I'd appreciate your feedback to do that. The last thing, I guess, my duty to tell you is to remind you the finals on May 11th. So please let us know, as soon as possible if you have any weird conflicts, like two or three exams on the same day. Okay. Fran is asking, what is the distribution of content on the final? Equal material from throughout the semester, or is it more focused on newer material, stuff covered after exam 4 that we have not been tested on? It's a good question, Fran, and I wish I wish I was better at planning these things out ahead of schedule. I haven't written the exam yet. There will be some content of things that were not on the last exam. But if you think about it, most of the stuff that we've done since the last exam is kind of conceptual applications of stuff that was on the previous exam. If I'm really honest about it, the action potential and the EKG. I'm not trying to make you guys biologists. I really just want you to understand the physics part of these. So there will be some questions on that, because we spent a good week or so talking about this stuff. But really, if you're grounded well in potential and electrical fields, none of this is anything more than an application of the things that you've seen before. I hope that answers your question, and I hope that we can get something posted to give you some more guidance on what exactly will be on the exam. But I haven't written it yet, so I can't answer you honestly what the distribution will be yet. Will we have practice problems? Excellent question. I think that's a good point. Yeah, I'll try to do that. I have to talk with Dawn, and there's no more group works, so we can't do our normal way of doing this. But that's a good point, and I'll talk with Dawn about how we can facilitate that properly. Maybe with some mastering physics, an extra optional practice set on mastering physics. let me talk to Dawn and see what the best way of us doing that is. Okay, and Peyton says, thank you, you're very welcome. Catherine, I see the 2 carrots. Is that, I think that's a good thing. I hope that that means like thumbs up or something. I'm not really good with emojis, but I hope that means, you know, good. And you're very welcome. So with that, I think that's about as much. How would you recommend studying for this, says Fran? Would you suggest working on previous exams and group works? Yeah, so other than this little bit of new material, Fran, I think, you know, we're trying to just make sure that you've retained and understood some global understanding of the stuff. So I would look back at old group works and old exams. I think that's, it just means that I also want, okay. So that's good to know, Catherine. If I ever want to tell someone that I want practice problems, I'll do those 2 carrots. And I second Cassandra's comment. Thank you for a good semester. You're very welcome, Cassandra. You're very welcome, Peyton. Thank you guys for a good semester. I've, you know, strangely enough, I've enjoyed it. It's a weird transition to online, but I enjoyed when I was working with you guys in person, and I've enjoyed this part of it as well. Good luck to all of you. Okay, just finished my last class of undergrad. Thank you for a great semester. You're very welcome. Very welcome. Okay. Yes. You're popping it out of my virtual background here. So, all right, let me turn this off. All right, so that's it, guys. Have a great semester, and if you have questions about the final or stuff like that, please don't hesitate to ask me, and we'll answer those. Otherwise, have a great day and good luck. Yeah.
So I'm sorry it was so long because
I'm still teaching class right now. I'll talk to you right afterwards, okay? All right. I'll talk to you right afterwards.
Okay.